and they can help. And the way you set it up is like either a 3x3 or a 3x4. There's like a certain rule in order to set up like a bunch of numbers by that 3x3 grid, and basically it solves systems of equations.
Great. Okay, so yeah, so you covered a lot there. So let's see. Yes, so these are things that computers use, and that's very true. They can be used to solve systems of equations of any dimension. So on the SAT, we only concern ourselves with 2x2, so two systems. Two equations and two unknowns. But you can use in principle matrices for all sorts of things, like n dimensional systems. Okay. So last time we talked about like a system. So for example, like something like this, like a 2x2 system of equations. One second. Okay, I'll get back to this. Caleb, are you here? Did you make it?
Yes.
Okay, great. I'll read your email in just a bit.
What's Kalave?
What's that?
Oh, nothing. Sorry.
Okay, so we talked about what are the three possibilities of two lines of a there. So you can have two general.
0 solutions, one solution, infinitely many solutions.
Yay. Okay, thanks. One, and what's the last option?
Infinite.
Yes. And so what does 0 solutions correspond to? What do the lines look like?
Parallel.
Yes. So like that. Okay, those are not parallel. Okay, one solution.
Like intersecting.
Yeah, and who's speaking right now?
Audi.
Okay, Adi, I really appreciate you talking, and I want you to keep talking, but I want other people to participate too, because people are complaining that like only a few of us are talking. So, so anyone besides Adi, what does one solution correspond to?
Just a straight line.
Okay, so we have, first of all, we're talking about systems of equations, and our case has to do with two lines. So what is the relationship between the two lines? So for example, they can have two different slopes and two different y-intercepts. These are two generic lines.
Perpendicular?
Sure, they can be perpendicular, but more generally, let's see, people have
they intersect at one point.
Yes, and all that is required is what about these two lines for them to intersect at one point?
They have different slopes.
Very good. Yes, so you can
Negative
have generally.
reciprocal.
Go ahead.
Negative reciprocal.
Sure. So in this case, if we were talking about M1 and M2, in this case, M1 is the negative reciprocal of M2 and vice versa. But this is not required for there to be one solution. This is what Euclid said, that any two lines that are not perpendicular will at some point cross. Even if you have like lines that are, okay, even lines that are almost slightly not perpendicular. You know what I mean? Like even, I can't draw this well, but at some point they'll converge, right? They'll meet each other here. Make sense? So they can be anything but perpendicular. I mean, they can be anything. They don't have to be perpendicular. And how about the infinite case?
They're the same line and has the same slope.
Yes, exactly. So more than them having the same slope, they have the same. You can have two. So these two lines have the same slope, right? And they have 0 solutions. But if you have what is true about two lines that have an infinite number of solutions? Not only do they have the same slope, they have the same
y-intercept.
Yes, and so sorry. People are messaging in the chat, and yes, Matthew, you're right. Okay, and Alexis, you made the same mistake. Yes, you're right that they have the same slope, but this is also, same slope. Okay, anyway, you get the point. This is basically the same line twice in a system, right? Okay, so let's just review what we know using this example. Okay, I'm going to do it very quickly, and I'm going to use the method of, what method do you guys want to use?
Substitution.
Substitute.
So I'm going to substitute 1 into 2. Okay, so this is going to go in here. So 3x plus 8 is 4x minus 6. And I'm going to subtract by 3x on both sides. I'm going to get my x's on this side. So x is, 3. So at some point, I'll give up on like telling you how I'm doing algebra, because I would hope that people know how to do this kind of thing. So x is 14. Now, how do I find y?
Plug the x back into one of the equations.
Yeah, so can someone tell me what, I'll put it into the first one, because 14 times 3 is easier than 14 times 4. What is 14 times 3? Can someone just do it?
42.
42 plus 8 is y. And what is that?
50.
Good. So my solution is this. Yay? Okay. So now we're going to develop an entire new way to do this. This may look very simple, and you may ask, why would we ever want to have another way of doing this? Well, the reason is that suppose you have like
The matrices.
yeah, you can have a 4x4 system. You know what I mean? So I don't know, z plus double. I don't know. I'm just making this up, right? So you can have a 4x4 system. This is a lot harder to think through. The way we just thought through this, like the thing to substitute here is easy, and we basically have, two unknowns. It's 2 variables and 2 unknowns, right? So you just want to get rid of one variable, reduce it to an equation that's 1 unknown and 1 variable. One equation that's just one unknown, which is solvable, which is what we've been doing since 6th grade. But here, we would like to find a more generic way of solving these types of problems. So the more elegant approach involves this entire field of math called linear algebra. And this is a huge field that many of you will study in college. And we're not going to cover like the real it's actually very abstract. We're not going to cover what's actually really going on, but I just want to introduce you to the big ideas. So there might be like 1 or 2 questions on the SAT. So this is really not a big SAT topic, but this is a huge sort of life topic, okay? This is like, you should know sort of.
Tiene 45 niños.
Okay, so I don't think that's relevant. Okay, so first we have this notion of the vector. So usually in life, we're used to numbers. Can someone give me your age, for example?
14.
Okay, so someone is 14. So this is a number, right? It's just it stands by itself. You can add numbers, you can multiply numbers, and we learned that these operations have inverses, like subtraction and division. So numbers, we've studied for a long time. Sometimes numbers are called scalars. So just get used to this terminology. A scalar is a standalone number. It's just a number so I'm 21. So scalar. Okay? Now we're going to introduce the topic of vectors. Okay, so vectors are lists of numbers. And I should be, a list is kind of not a mathematical, okay, so someone else said there's 14, great. A list is not a mathematical description of anything. I mean, don't use the word list. It's just it's an informal way of describing what a vector is. But for example, okay, let's see, can 5 of you give me your age? I need 5 people to volunteer and give me your age.
16.
Okay.
16.
15.
14.
14.
17.
Okay, 17, and someone else said 15. So this is a vector, okay? And how many, so vectors have dimensions. So say I'd left out this 15, then I would have a vector like this, 16, 15, 14, 17. This vector has how many columns? How many columns?
1,
It has one column, and how many rows does it have?
4,
4.
4 rows. So we denote vectors and matrices using this format of rows by columns. Okay, so how many rows does this have?
4.
5.
5.
Oh, 5.
Yeah, be careful. I screw this up too, so how many columns does it have?
1.
1.
Yay. So these vectors are of a different nature because they have different dimensions. So this idea, so do you have a notion of dimensionality? Okay, I erased the numbers, but someone said there were 14. Does 14 have a dimension to it, like a sense of dimensionality?
No.
Not really, because every number is technically a 1-by-1 vector. You could write it in these parentheses like a vector, and see there's like 1 row and 1 column. So scalars are by definition like 1-by-1 vectors, but we don't even call them vectors because all scalars are 1-by-1. But vectors can have any number of rows. However, all vectors only have 1 column. So get used to, when you see vector, get used to there being 1 column. Okay? Now matrices, what happens if I do have multiple columns? Then I get a big, like a grid almost of numbers. Okay, so now I need more volunteers. Tell me your ages. Just shout it out.
14.
16,
14, 16,
15.
15, more.
17.
18? More. Keep going.
17.
17.
16,
Okay, yeah, some of these will repeat. It's okay. Come on.
16.
Okay, a few more
16.
16s and someone else. It doesn't matter.
15.
15. Okay, great. So
14.
this is a nice little matrix that we've constructed. What are the dimensions of this matrix? How many rows are there?
3,
3.
3.
And how many columns are there?
3,
3.
3. So this is called a 3-by-3 matrix. And this is you'll get very used to writing matrices like this, okay? Because 3-by-3 matrix, how many dimensions of space are there?
3,
3, right? We live in 3-dimensional space. And so you can imagine that like in physics, engineering, like all sorts of, any physical application, if you're doing like a mechanics kind of problem, 3-by-3 matrices are everywhere, okay? So you'll get very used to this. What if you're confined to the plane? What kind of matrix would you intuitively, so say I have like some little ball rolling on this plane.
Calculus.
What's that?
Calculus.
So I'm asking what dimension, how many dimensions are in a plane?
2 dimensions.
2.
2.
Yep. So you would, in doing 2-dimensional problems, you might expect to use, I'm just sort of generically talking right now. This is not anything kind of profound, but you'd be using kind of 2-by-2 matrices, okay? And then the simple case of the line, how many dimensions are contained in a line?
1.
And this is the type of physics and engineering and math that you people are very used to. Like in your basic, physics classes or chemistry or whatever, everything, is all motion is decomposed into, just 1-dimensional components, right? So like even a parabola, even something going like this, you decompose this into X and Y, right? I said that backwards, X and Y. And each of these is like, motion along a line, right? So and this involves scalars because 1-by-1, technically 1-by-1 matrices are scalars, but we don't call them matrices, we call them scalars or just numbers. So the goal of so much of college and the rest of high school for many of you will be going from this simple stuff to slowly talking about motion in the plane, and maybe in college talking about motion in 3D. And each time you go from one of these to the other, things get very like entangled. It gets a lot harder. Okay, so people are okay. I'm gonna get back to these emails later. Okay, so how do we add matrices? So I'm gonna use 2-by-2 matrices to describe this discussion. This should be very easy. I'm just gonna make up some matrices. How do we add matrices? Does anyone want to take a guess as to how you would add matrices?
Wouldn't you add like the first like 1 to 4, or
Yes.
then 0 to 5, and then 2 to 6, and then 7 to 3?
Yes. That is exactly how things go. It's kind of
Corresponding numbers.
corresponding numbers. So this is the first, this is the first row, first column. This is the first row, second column. This is the second row, first column. This is the second row, second column. And so you're going to add the first row, first column with this first row, first column. You're going to add the first row, second column with this one, so on and so forth. So you just add the corresponding numbers and your dimensions are preserved. So this is a 2 by 2 matrix. This is a 2 by 2 matrix. And this should also be what?
2 by 2 matrix.
2 by 2.
2 by 2
Yes.
matrix.
So what is the first element?
5.
What is this element?
5.
Yes. What is this element?
8.
8.
What is this element?
10.
10. So you see how this is just like I mean, this is just addition, right? So let's just do a subtraction problem. It's the same thing, right? If you can do addition, you can do subtraction. So 3, 1, minus 1, pi, I don't know. Minus 3. I'll make it kind of, yeah. Let's see. I don't care. 0. And 2 pi. What would the answer here be? So first of all, what's the dimensions of this matrix?
2 by
2
2.
by 2.
By
2
2.
by 2.
Yes. And what would the first element be?
6.
0.
Yes. Very good, because 3 minus 3 is 3 plus 3, which is 6. What's this element?
4.
2.
2.
1 plus 1 is 2. What is this element?
Negative 1.
Negative 1.
Yes. And what's the last element?
Negative.
I.
Negative pi, because pi minus 2 pi is negative pi. And Alexis said 3 by 3. I don't know what you mean, because we're dealing with 2 by 2 matrices here. Okay. How do we multiply? So now, okay, so Alexis, that was way before. Okay, sorry, I just didn't see it. Okay, so how do we multiply matrices? Multiplication of matrices is a bit more tricky than adding and subtracting matrices. And so this is going to be the new part for many of you. And this is going to take a little bit more getting used to. And don't worry, okay, please don't worry if this doesn't make sense. This is really just introductory. I just want to get you exposed to sort of the big ideas. So if the little details don't make sense, don't get caught up in them, okay? How do we multiply matrices?
I'm guessing now if you're multiplying, then you take the entire first row and then multiply it by the multiples, like A in this situation, probably.
Okay, that's sort of I think you're kind of getting at it. So you're suggesting taking this first row and multiplying it all by A. So basically you're thinking it'll be like A and 0. Is that?
Yeah.
Okay, that's not quite. That's a good guess. That kind of follows the pattern that we did in, in the previous in addition. But it turns out that it's not really the way.
You multiply the A by 1.
Multiply the A by 1.
Yes.
So right. So first let's talk about here. I didn't fill in this number. Let's let it be 3 or something. Actually, let's let it be 0 so you can see something. Okay. You're saying, okay, so the way this works, I'm going to teach this to you like it's a rule, and it's going to be kind of strange, but when you get used to it, it'll be like second nature. Okay, Alexis is saying, I think you cross multiply. Okay,
like
well.
Scalar?
I don't know what you mean by cross multiply. I'm going to sort of rationalize this in terms of dimensions, okay? So matrix multiplication, you can't just multiply any two matrices together. You can only multiply matrices if the number of columns of this first matrix, which is 2, matches the number of rows of the second matrix, which is 2. So this is a criterion for matrix multiplication. These numbers have to be the same. This is just a rule. So for example, if I had a 3 by 3 matrix and I tried to multiply it by a 2 by 1 matrix, is it possible?
No.
No, because this number is not the same as this number. The number of columns in the first matrix, the number of these, has to be equal to the number of rows. Sorry, not these. The number of these. This is the number of columns. See, I messed up. The number of columns has to be the number of rows of the second matrix. And 3 is not equal to 2. So you can't do that. So that's the first criterion. What is the dimension of the answer? The dimension of the answer is given by the number of rows, so the number of V's, truly this time, and this number, which is the number of columns of the second matrix. So your answer is going to be 2 by 1. So say, right, so 2 by 1. So say I was multiplying.
Wait, why is it 2 by 1?
Okay, so here's the rule. I'll just write it generally. If you have an A by B matrix and you try to multiply it by a B by C matrix, your answer will be of dimensions A by C. A, C. This is sort of the rule. You'll understand why when you want really study linear algebra. Okay. So is it possible to multiply? So here, what if you have a 3 by 2 matrix and you tried to multiply this by a 1 by 3 matrix? Is this possible?
No.
No. Why?
Yeah, no.
Because
the
number
2 and
of
1 are
columns in the first.
Yes, because
column
2 does
doesn't
not equal 1.
correspond with
These numbers need to be the same. So you can't even do this. What about 3 by 3 times 3 by 4? Is this possible?
Yes.
Yes.
Yes, because 3 equals 3. What is the dimension of your answer?
3 by 4.
Yes,
3
your
by
answer will
4.
be 3 by 4. And so it'll have, 3 rows and 4 columns. Make sense? So we're just talking about the size of the solution, so to speak, right? The size of the product. Now, how do you actually do it? This is where, okay, you need to sort of really focus, okay, because it can be confusing. You take this number, you multiply it by this number, and then you add that to this number times this number. So in other words, and that gives you this element, right? So this element here of this matrix is going to be 1 times A, right? This times this, plus 0 times B, right? And now the bottom element is going to be, you do the same thing, just with the bottom row here. So 0 times A plus 1 times B. And so what does this equal? What's 1 times A? A. And what's 0 times B? 0. What's 0 times
A over B.
0. Yep, and so this is B, right? 0 times A is 0, 1 times B is B. Make sense? This is so the product of this matrix is AB. Yes?
Yes.
Great. Okay, so what I'm really trying to show you, okay, so this was actually multiplying a matrix by a vector, because this is, this, whenever you have a 1 here, this is a vector. So this is kind of simple, actually. What happens if you have a 2 by 2 matrix multiplied by a 2 by 2 matrix? And this is what we're going to really be, this is what might challenge people more. What's your answer? What's the dimension of your, first of all, can it be done?
Yes.
Yes.
Because 2 equals 2. What's the dimension of the answer?
2 by 2.
Yeah. And so now, what do? I'll kind of guide us through, because this is only the second one we're doing. We're going to do, so there are going to be 4 elements here, right? When you have a 2 by 2 matrix, you're going to have 4 elements. 1, 2, 3, 4. So this first element is given by 1 times A plus 0 times C. So 1 times A is A, 0 times C is 0. So this is A. Your second, this element is given by this times this. Sorry, losing my mind. This times this plus this times this. So 1 times B. Yeah, go ahead.
Maybe you should change the colors so people
Yes,
get it.
thanks. I will. So your second element is this times this plus this times this. So 1 times B is B, 0 times D is 0. So this is B. Your third element is green. Your third element, what's wrong with this computer? Your third element is this times this. So I'm talking about this one now. This times this plus this times this. So A times 0 is 0, plus 1 times C is C. Your last element is this times this, plus this times this. 0 times B is 0, 1 times D is D. Sorry, I didn't use a different color, but does this make sense? Roughly?
Yeah. It's
Okay, we're
pretty
gonna do
simple.
some practice. I know it seems really ad hoc and like really kind of random at this point, but let's do some practice, okay? So the first one, how would we do this? So this is 2 by 2, this is 2 by 1.
So it would just be 1 times 1 plus
So first of
0
all,
times
let's
2.
ask the big questions. Can it be done?
Yes.
Yes, because these numbers are the same. What is the dimension of the solution?
2 by 1.
2 by 1.
And
I have a question.
go ahead.
So what's the solution if it can't be done?
There is no
solution.
That's a good question. It's actually a really good question. It's not even. It's like you wouldn't. Nature doesn't accommodate matrix multiplication that can't be done. It's not. Nature doesn't work that way, and math doesn't work that way either. So you'll never. It's a good way to see if you're doing something right if you've set up a problem right in terms of your dimensions. But if you're doing something right, you'll never have like a 2 by 1 matrix multiplied by a 2 by 2. These numbers will always be the same. That's just the way nature works. It's actually really interesting. Okay, so you'll never in your life, if you become an engineer, a physicist, or a mathematician, or whatever, you'll never have. Don't worry, like the world won't crumble. Okay, so how do we do this? You're gonna take this
1 times
times this plus this times this, and that gives you this first element. So this is 1 times 1 plus 0 times 2, which is just 1.
1.
0 times 2 is 0. And now the second element, you just do the bottom with the same operation. So 0 times 1, and I'll use a different color. 0 times 1 plus 1 times 2 is, what's 0 times 1? 0. 1 times 2 is 2. Yay.
2.
Make sense?
Yes.
What do you notice, actually, about this matrix, 1, 0, 0, 1? When you multiply it by anything, what did it give you?
The vector.
It gave you the same thing. See, we multiplied 1, 0, 0, 1 by AB, and we got AB. Isn't this a lot like when you multiply something by 1? What is 1 times A?
A.
And what is this property called?
Identity.
Multiplication.
Yes, identity. Identity of multiplication. Sorry about my spelling. Yeah, so 1 is the identity element. That's what we call it. And so similarly, can't spell. Similarly, look, 1, 0, 0, 1. This is the analog, sort of the analogous quantity of 1 in matrix math of linear algebra. So 1, 0, 0, 1 is called the identity matrix. And this is what we generally call it. And sometimes, instead of just calling it 1, 0, 0, 1, people will call it I, and they'll give it like a kind of bold face. And sometimes you'll even see it like this, just 1. Because it really is like the analog to 1. I had a quantum mechanics instructor who used to call it 1. And I liked it because, yes, it preserves your vector, just like 1 preserves your scalar under scalar multiplication. Okay? Great, let's try this. So I know this is fast-paced. Again, if you don't follow, it's okay. It really is this is something that I really struggled with in high school, and you just have to do a bunch of these problems. But I hope that coming out of this lecture, you'll just know what a matrix is, what a vector is. You might remember how to vaguely multiply them. Okay, let's do this. So what is the dimensions? 2 by 2, and what's this dimension?
2 by 1.
And what's the solution going to be? Dimension.
2 by 1.
2 by 1. Sorry, 2 by 1. So you're going to have something here, and you're going to have something here. Okay, so 1 times 7 plus 1 times 15. That's 7 plus 15.
22.
Yeah, so that's 22. Now for the bottom element, 0 times 7 is 0, plus 0 times 15. That's just 0. Make sense? Okay, now I want someone to do this one without my help. Just tell me what the answer should be. So do exactly what I just did. What are the dimensions of the solution?
5
2
over
by
9.
1.
2 by 1.
2 by 1. Very good. And what is this element equal to?
5.
Okay, so what you did is you did 2 times 1 plus 3 times 1, and you indeed get 2 plus 3, which is 5. What's this bottom? Someone else. What is this bottom element?
9.
Yes. 4 times 1 plus 5 times 1. That's 4 plus 5, which is 9. Very good. Okay. Great. So now let's do one last example, and then we'll apply this. Then all this will come together in the sense of linear equations. Right now, we're just talking about the mechanics of sort of how matrix multiplication works. But we'll talk about the meaning, okay, soon. So now let's see. Can someone else who's brave do this one? What's the dimension of this?
2 by 2.
Yes, and you figured that out because this is 2 by 2, this is 2 by 2. So this can be done, and the outer numbers give you the dimensionality. So what does this number equal? What is the first element? Take the first row.
3.
Yes. Is it 3?
4.
No. Okay.
1.
So let's just do it.
No, it's just 1.
It's 3 times 0 plus 1 times 1. 3 times 0 is 0. 1 times 1 is 1.
1.
You add them, you get 1. What is this element?
It would be 1. Oh, wait. No, that would be 3.
Yeah. 3 times 1 plus 1 times 0. That's 3. What is this element? Now you use the bottom row. Minus 1 times 0.
1.
Plus 1.
1.
That's 1. What is the last element?
-1.
Oh, this is a cool pen. Yeah, it's -1. You do. Why is it not writing? Okay, now it's writing. Yeah, -1 times 1 is -1 plus 1 times 0. I don't know why it's not right. Okay. Yeah, so it's -1. Okay, I'm not going to use this pen because it's slow. Okay, does it make sense? You kind of have a basic understanding?
Yes.
Yeah.
Okay, and then just looking at this last answer, you had 3, 1, minus 1, 1. When you multiplied it by this matrix, which kind of looks like the matrix, but look, all that's different is the zeros and the ones are flipped. So what happened with this matrix? Look, 3,
The numbers
the
are
first, yeah, the numbers flip.
the numbers flipped. So in other words, we just flipped the rows and columns. So the original matrix had these flipped. So the 1 became here, and the 3 became here.
So if we can like memorize these like properties without even having to do it, we can like do the
Yeah, in fact, it'll just happen by itself. When you see this matrix, you'll be like, oh yeah, that just means flip the rows and columns. It'll just happen. Yeah, you don't even have to worry about it. That'll happen naturally. Okay, so how can this apply to linear equations? Generally, are all the linear equation kind of the system of linear equation problems that we were doing were of this form. So they were, ax plus by is c, and cx plus dy is e. This is not slope-intercept form. Be mindful. This is not slope-intercept form. This is written in a form that is nice for matrix multiplication. Okay. Okay. But this can be written in, for example, if you take the first one, if you wanted to write it in slope-intercept form, you would write by is minus ax plus c, and then just divide by b. So, sorry, this is c. Divide by b, so minus a over bx plus c over b. This would be in slope-intercept form. So what I'm saying is just be mindful. This is not in slope-intercept form, but this is in a form that is very useful for our discussion. So I would like to propose to you that this thing right here, this system, can be written as matrix multiplication, specifically in this form. Does anyone kind of see the pattern of why I selected it like this? Look, I took the coefficients, which are the numbers that are multiplying the variables, and these formed the matrix. Look, A, B, C, D. These form the matrix. And then the variables themselves, x and y, form the vector. And then the right-hand side, so to speak, is the right-hand side here. And let's verify that this is the same, that we get the same kind of thing. So what So how would you do this? How would you multiply this out? First of all, what's the dimension of your answer?
2 by 1.
2 by 1.
2 by 1, right? Because you take the outer number and the inner. And you know that this is like a valid problem because the dimensions of the inside numbers match. So yeah, 2 by 1. And now what would you do? Here, let me scoop this.
Multiply a by x and b by y.
Yep, so a times x plus b times y is the first element. And what's the bottom element?
cx plus dy.
Very good. So I know to some of you, like, you're going to take some time. I was always like the slow kind of student. I would take forever to like learn these like kind of mechanical things. So some of you will like take some more time, but this is not on the homework. Don't be like worried. This is not on the homework. You should I've taught everything that is on the homework. Okay. So it's okay if this doesn't quite make sense, but can you see that, and this, this is CE. So can you see that there is an equivalence between this and this? Look, AX plus BY is C. CX plus DY is E. That's exactly what's written here.
Will it always be in that form in the SAT?
It'll always be, well, you might be given something in this form. You might be given some like 2 equations in slope-intercept form or in point-slope form. You should be able to manipulate within those forms. But the SAT people will probably not give you questions in these forms. But you can always convert, right, between this and this as well. So this is just another method. I'm about to introduce to you another method of solving linear equations. So we talked about substitution and elimination and graphing. Well, now I've written the system of equations problem as a matrix multiplication problem. And this is the matrix multiplication problem. Sorry. What I just wrote is the matrix multiplication. So if we can solve this, we want to find x and y. This is the solution. This is like this is what we used to write as like the ordered pair. That's all this is, this vector. That's our solution. So if you can find what this solution is using some matrix methods, then you're done. That's your solution. Okay? Make sense?
Yes.
Okay, I know I'm going fast. The Thursday lectures will generally be a little faster because the Thursday lectures will not be covered. It's not material that's like on the homework, and it's probably
that week.
Yeah, well, because I want to give you time to do the homework. So all the homework sort of material will be covered by Wednesday. Thursday will sort of be good for just exposure and sort of stuff that'll help you in school as well. Stuff that'll be interesting to the juniors and seniors especially. So don't worry if this isn't quite making sense yet. This is pretty abstract. So basically we have this problem, AB times CD times XY is CE, and we want to solve for XY. Now I'm going to draw your attention to an analogy, to the scalar algebra analogy of AX equals B. How would you, if this is a scalar, these are just numbers, how would you solve for X?
Divide by A.
Yes, and what would you get?
B over A.
B over A. And now note that you could write this as this. What is A to the negative 1? By definition, that's
1
over A.
Yeah, 1 over A. So, and this is actually the notation we use for matrices, A to the negative 1, so to speak. So this is the analogy for scalar case. Now, let's apply that to this situation. This is the problem, right? A, B, C, D. I showed that this is equivalent to the system of linear equations. So let's apply that. So let's call this matrix A, that was the analogy here, right? A. So this is our matrix. And this is like your solution, right? We were looking for X. Similarly, now we're looking for this vector X, Y. And your right-hand side, B, is like your CE. Okay? So calling this entire thing A, I would rewrite this entire equation as this. A times XY is CE. And remember, from the solution to this case was this. Similarly, where A is just 1 over A. So we need to find an analogous sort of 1 over A quantity for this A. If we can, what you really did here in this problem is you divided both sides by A, and you knew that A divided by A is just 1, right? That was your reasoning. You know, A divided by A is 1. So the only thing is we can't really divide by a matrix. So you can't, so when you have a matrix equation, you can't just divide by a matrix. Matrix division is not defined. But there is an analog, okay, to division. And the analog to division is the multiplication of an inverse, what is called an inverse matrix. Okay, so someone has messaged in the chat. Multiply by, yes, I did, you're right. Yeah, multiply by the inverse. I'm guessing you've seen this before. But the rationale is actually pretty, this is pretty abstract, okay? So I'm making analogies to like scalar and, you know, vector algebra. So this is, take some time, you know, I'm gonna post this lecture on YouTube. I'm recording all this. So you can rewatch this if it doesn't make sense. If you don't care about it, that's fine too. You'll do fine on the SAT if you don't know this, okay? So if I can multiply both sides by A inverse, then A inverse times A would give me the analogous 1, but that's what we call the identity matrix. Remember the identity matrix? This is what some people like to call I and what some people like to call 1. Well, now you can see the utility of calling it 1 because it makes a direct analogy to the scalar algebra case where where any number divided by that same number is just 1, like the scalar 1, right? So if you can, so A inverse, we need to find what is A inverse? If we know what A inverse is, then we just multiply the entire equation through by A inverse, and A inverse times A is the identity matrix, 1, 0, 0, 1. And we know that the identity matrix times xy is just xy. And so our solution is A inverse times CE. So this is our solution. And all we need to do now to find our solution is find A inverse. Does this make sense? This is the hardest part of the lecture.
Yes.
Kind of.
Kind of, okay. What is lacking right now in like your understanding? What is confusing?
Just the end part of it.
Just the end part of it, okay.
The end part, yes.
Okay, let me just summarize very quickly, like in a minute. Okay, so we have A, B, C, D. And I showed, I said, okay, this is equivalent. If you're given this system, AX plus BY is C, and C, come on. It's very slow. CX plus DY is E. This is your given system of linear equations. I showed by just multiplying out these matrices, you know, that these things are equivalent, right?
Yes.
You were on board for that?
Yes.
Yeah. Okay.
Yes.
Then I said, now remember the analogy to scalar math, like the math that you're used to, that you've been doing your entire life. And if, say you had this problem, AX equals B, how would you solve for X? Well, you said you would divide both sides by A, right? Because you want to isolate X on one side of the equation. That's the entire like essence of algebra, right? You're isolating variables. And dividing by A, well, that's the same thing as multiplying by A inverse. You know, right? Are you familiar with this notation?
Yes.
Okay, great. So any, like the negative exponent, and I'll use a generic like alpha. Alpha to the -1 is 1 over alpha by definition. These 3 lines mean by definition. So I can also just write this as A inverse. Okay, and I'm going to write it now. And this is just 1 in the case of scalar algebra. 1 times X is, you know, 1 over, this is just 1 over A times B. And what is 1 times X? That's just X. And this is just that. So this is the, you know, this is the scalar algebra case. The linear algebra, like the vector algebra, the matrix algebra case, we can call this thing A, and I'll just keep this in this form. XY is CE. I've just defined this matrix to be A. And now I'm saying that I haven't developed the inverse yet. I haven't told you what the inverse is, but I said, if there is a thing that is analogous to this, like 1 over a, and let's call it the same thing. Let's call it a to the negative 1, or a inverse. That's what it's called. If it exists, then a inverse times a, if we multiply the entire equation, this entire equation through by a inverse, then a inverse times a would be your analogous 1, right? Here you had a inverse times a being your scalar 1. This is like the number 1. This is your analogous 1, which is actually the identity matrix, right?
Yes.
And then, so a inverse times a is 1 times xy. But we saw like like a few examples where when you multiply by the identity matrix, you're left with the thing you're multiplying with.
Oh.
Do you remember that? Right? Because
Yes.
look, you can verify 1 times x is x plus 0 times y is y. So your first element is just x. Same thing here. 0 times x is 0 plus 1 times y is y. And so this is your solution. That's all I'm saying.
Oh, okay.
Make sense?
Yes.
Great.
Now it does.
Okay, so now what is the inverse? That's the question, right? So we said that a inverse times a is just the identity matrix, 1 times xy, and this is a inverse times ce, and the identity matrix, this is just what I said. The identity matrix times xy is xy, and this is your solution. So what is this? If we know this, we're done. It turns out that the inverse is given by this expression right here. Write this down if you can. This is the definition of the inverse matrix. And I'm not going to prove, I actually can't prove this to you because we haven't studied formally like the field of linear algebra. So just take this kind of on my word for now, but this is the inverse of A. So given the matrix A, you would basically multiply this times this, subtract it from this times this. That's what is in the denominator here. Then you would flip these two numbers, giving you D and A instead of A and D. And then you would put minus signs on these numbers. Yes? So just take this on my kind of as a fact for now. So let's, in the 2 minutes remaining, computer, so let's apply this to this equation. So first of all, okay, I know this is a lot, okay? So just kind of enjoy it for the ride if you're very lost right now. Just sort of ride the wave, okay? Try to find the things that are interesting, okay? This is the problem that we started the lecture with. I'm going to do this the new way, the matrix method way, and see if we get the same answer. And if we do, we'll say, hooray, okay? So I'm going to write this. We need this to be in the form ax plus by is c.
I have a question.
Go ahead.
So, like, one of the questions for this question, what would it say? Like, how would you know that you have to apply the matrix?
You don't have, you never have to. Okay, so on the SAT, you can probably do all the questions without this method. You on the SAT, this is a way to do questions, but it's probably not the most efficient way to do questions.
It's the easiest way for this.
Yeah, if you have like a 3x3 matrix or a 4x4 matrix, this becomes like the only way to do those questions often. So in college, and certainly like when you're a senior in high school and you're taking like a physics class, you'll come out with systems of linear equations and you'll say, oh, like this, let's just use this matrix approach. So it's really up to you. And you'll develop the wisdom by then to sort of know when it's right. Okay. Yeah. Sorry if that's not like terribly satisfying. Okay. Okay. So anyway, we need this to be in this form. Dx plus ey is for whatever, right? So right now it's in the other form. So I basically need the x's and the y's on one side and the numbers that don't have x's and y's attached to them on the other side. So I'll convert that to this form. So I'm going to put the x's and y's on the left side. So minus 3x plus y is 8. Minus 4x plus y is minus 6. Now I'm going to write this as a matrix problem. So this is kind of the crucial step here, right? So the numbers go on this side. This is just what we developed, and I showed that this is true to you. So and now I'm putting the coefficients. So the minus 3, there's a 1 here, right? 1 times y is y. That's what happened here. And then with these numbers, I'm going to put a minus 4, and there's a 1 here. And so this is going to be a 1. And then this is your xy. So now I just have to find the inverse. Okay, so I know we don't really have any time left, but I'll just calculate the inverse of this matrix. So I'm going to call this thing A. X times y is 8 minus 6, okay? And now A inverse, this is the other crucial step, right? You multiply by A inverse on both sides. And A inverse times A is just the identity matrix, which is 1, 0, 0, 1, which is just xy, which is just xy, right? And this is your solution. So all I have to do is find the inverse of this matrix, and I'm going to apply the property. And you can go back to your notes. I told you to write that down. Now I'm just going to apply that. So the inverse of A is 1 divided by, so this is just a formula for you. The proof will come later in life, okay? 1 divided by, I'm going to take this element times this element. So minus 3 minus this element times this element. So that's minus 4, and it'll become plus 4, right? So minus 4 is plus 4, okay? And I'm going to now multiply this by, the rule said to flip, to exchange these two numbers. So this is going to be a 1, this is going to be minus 3. And then to take the negatives of these two numbers. So this is your inverse matrix. And what is 1 divided by minus 3 plus 4 is just 1. So this entire thing is just 1. And this thing is minus 1, 4, minus 3. Now is the moment of truth. Now I need to multiply. This computer is so slow. Sorry, it's not like responding when I move the screen. Now, so this is A inverse. Now let's see if it works. If I put it in here, I better get the same solution that we got at the beginning of the lecture. And this is the matrix multiplication part, right? This is why we care about matrix multiplication. So your answer is going to be 2 by 1, because this is 2 by 2, and this is 2 by 1. So you can do the problem because these numbers match, and the outer numbers give you the dimension of the answer. And let's see. 1 times 8 plus minus 1 times 6. That's 8 minus 6.
2.
4 times 8, 32, minus 3 times 6, 18. What is this?
14.
6, 14.
Okay, we need the right answer. This is the easy part, right? You should all be able to do this. So 214. Let's now see. Did it work? Okay, it did not.
Wait.
Okay. I will send, okay, we're out of time. Did we do this right? Did I write the same equations? Okay, I will send you, or maybe we'll touch up on this on Monday. This was not satisfying because the answer didn't work out. 3x plus 8. Okay, well, I'm going to send you the attendance quiz. It doesn't cover any of this. It just covers like very basic, like what is a matrix, what is, just like definitional things, okay? So even if not much of this made sense, that's okay. This is really for exposure. It should just kind of show you where the future is for many of you in terms of math. Maybe refresh some things for others, maybe introduce some things for others. So I've just sent the quiz out. Go ahead and get started. In the meantime, I'm going to figure out what I did wrong here. And you're welcome to ask questions. So I just sent the quiz. It's on the chat. Let's see. Any questions?
So this class is till 10 to 11?
This class is 10 to 11, that's right.
Okay.
Yeah.
Thank you.
Every Monday through Thursday. The reading class is 9 to 10, Monday, Wednesday.
Okay. Thank you.
You're welcome.
So there's no class tomorrow?
There is no, that's a very, I should have said that earlier. There is no class tomorrow. I have office hours tomorrow, and I think that'll be 10 to 2, and I'll send like a link. And I'm just going to do my own like work, and if you have questions on the homework or whatever, you can just come by. Any other questions? In the meantime, I'm going to figure out what the heck went wrong here.
Thank you so much.
Oh, you're welcome. Thanks for tolerating the tech issues today. I would have gone slower, but I guess kind of had to get through in the time we had.
Sir,
Uh-huh.
I forgot to put my name on my quiz.
What's your name?
Julia.
Julia. Okay, that's fine. Oh,
Okay,
got it. Yeah.
thank you.
Sure, you're welcome. What is your feedback? I mean, can people just tell me like
I got a 5 out of 5.
oh, good. Okay, so okay, that's the goal. Great. And how do you feel? I mean, how do you feel about what we just talked about?
The multiplication was really confusing,
Okay, that's good to know.
but I got like the important stuff that you said we would need,
Great.
like the labels and everything. So that helped me on the quiz.
Sweet, sweet. Okay, I'm glad to hear. And other people are messaging me and they said they got 5s. That is great.
Hello.
Yeah, whoever's talking right now has like really bad feedback. But go ahead. I'll try to decipher what you're saying.
Hello.
Yep, that sounds better. Go ahead.
Okay, so my question is, where can I find the link to the reading and writing meeting, Zoom meeting?
The link to the Zoom meeting?
Mm-hmm.
Okay, so Pratik is in charge of the entire Pratik is in charge of the reading class. Okay, so email him. He has a meeting ID. Okay, and okay, let me send you Pratik's email. Okay, so I'm gonna stop the recording.